Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 10th grade topic, finding missing sides and angles using the law of cosines. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use that to skip ahead to whatever part of the video interests you the most. If you have any question about what you see here today, or even your own homework, remember you can always put them in the comment box below. I'd love to be able to help you as much as I possibly can. However, if the comment box below is a little bit too small, feel free to visit me on Facebook at Tutor Me Sempai and tell me all about it there. When you find this video helpful, remember to leave a like. It really helps the channel get these videos out to more people who may need some help. And while you're at it, remember to hit the notification bell, smash the subscribe button, and share this video with a friend. But without further ado, let's jump right into some law of cosines. So if you hadn't seen my video on the law of sines, I really recommend you check that one out because the law of sines and the law of cosines really do complement each other when you're trying to tackle these triangles with missing sides and missing angles. So although the law of sines and the law of cosines don't really depend on each other, it's really good to have a foundation built in both of them. So I'll be putting a link to my video on the law of sines right above here. So what is the law of cosines? Well, the first thing we have to do is draw a triangle. It's really good to kind of get a picture because the law of cosines has a few parts and it actually has 3 different faces. So let's start with drawing our triangle. So here we have a very generic triangle where the uppercase letters are the angles and the lowercase letters are the sides. And if you recall from my video on the law of sines, we did something very similar when we were trying to map out how to use it. We're going to see that in a little bit as well, but I wanted to kind of get the formula down first because how to use it is going to naturally fall into place afterwards. So this is what we have when we're talking about the law of cosines, this kind of triangle here. And the formula that the law of cosines uses is as follows. C squared equals a squared plus b squared minus 2ab cosine big C. So that's going to be the angle here. You're not going to find cosine of a side. That's the angle here, big C. So notice we have a side here, c squared, equaling the sum of the squares of the other 2 sides minus 2 times the sides multiplied to each other, so times AB times cosine of an angle here. So this is the law of cosines formula. And I said it has 3 faces because technically you can use this formula for any angle within this triangle. So we did one for angle C. We can also do one for angle B. And you will see a very nice pattern here. So for angle B, we're going to have b squared instead of c squared here, a squared plus c squared. So you see it's always the other 2 sides here. We have one side here, it's always the other 2 sides, and the same thing here, 2ac, the other 2 sides, cosine big B. So we have little b here, we finish it off with a big B. Little c here, finish it off with a big C. So the third face is going to use the other side and other angle. So that's a squared equals b squared plus c squared minus 2bc cosine big A. So you can use the law of cosines for any side and angle within this triangle here. And you don't have to really spend your time remembering all 3 of these faces. Just remember the general format and you can find out whatever face you need. So remember your pattern is you're going to sandwich everything between the 2 letters. One letter is going to be big and one letter is going to be small. Your small one is squared, your big one is attached to a cosine. And remember, it has to be cosine because it wouldn't be the law of cosines without your cosines. So you have a cosine with your big letter, you have your squared letter on this side, and everything in between is going to be the other 2 sides. So just remember your sum of squares minus 2 times each of the other sides times your cosine. So we talked about what the law of cosines is. As far as this formula is concerned, now we're going to talk about when do you specifically need to use the law of cosines. And once again, if you've seen my video on the law of sines, you see I'm actually doing this in reverse as far as the order goes, and that is very intentional because you're going to see things kind of fall into place. Like I said, they kind of complement each other, and wherever one lacks, the other one tends to pick up. So you'll see specifically for the law of sines, there were 2 cases that we couldn't really do anything about. And there was one case that nothing handled. So we're going to ignore that. And if you remember what that was, that's when you had a triangle with all 3 angles. That is not going to be handled by the law of sines or the law of cosines and finding those missing sides. It doesn't work. So we're not even going to talk about that one, but we will talk about the other two cases that the law of sines failed to address, because that is where the law of cosines shines and picking up the slack where the law of sines left off. So we had the triangle in which you had all three sides, so A, B, C. We had all three sides, but we had none of the angles. That was something that we couldn't use the law of sines for, but we will be able to use the law of cosines for. And there was another one in which you had a triangle in which the sides, so let's say A, B here, sandwiched the angle. So we had a side sandwiching the angle here. If you had this type of triangle, you also could not use the law of sines. But these two triangles are exactly what we need for the law of cosines. So you put the two pictures together, you have the law of sines handling three triangle types, and you have the law of cosines handling the other two. And that, like I said, that sixth one, no one addresses because we're not going to be able to do that. When you just have all angles, you just can't find your missing sides. It just, you don't know what kind of information you have. So the law of sines and the law of cosines handle the other five. And if you recall, we started with some notation as well, in which this was the side, side, side triangle, and this was the side, angle, side triangle. Side, side, side meaning you have side, 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 and side, angle, side meaning you have that sandwich with the sides, side, angle, side, and that is the triangle notation that is applicable for the law of cosines. So this is specifically when you're going to need the law of cosines. But let's talk about more in general, because there was one question that we had to ask during the law of sines that we haven't asked for the law of cosines. And that question was, do you have a right triangle? And if you recall, if you answered yes to that, I said you're most likely going to be using SOHCAHTOA or the Pythagorean theorem. And if you said no, I said you're most likely going to be using the law of sines, or they call it the sine rule as well, right? Or the law of cosines. Now, the law of cosines is also known by the cosine rule. So we already kind of answered this in our law of sines video, but there's a little bit more to this picture than just a simple yes, right triangle, you're going to be using these, no, right triangle, you're going to be using these. Because if you remember that formula looked very similar to something that you might have seen already, especially if you saw my last week's video. And that's the Pythagorean theorem. If we take the Pythagorean theorem, we have a squared plus b squared equals c squared. And if you take that first face that I showed you for the law of cosines, you have c squared equals a squared plus b squared minus 2ab cosine big C, the angle. Now, obviously you can rewrite this, so don't let that trip you up. You can always say c squared equals a squared plus b squared, but they look very similar except for this part here. And this is where the magic happens. Technically, you can use the law of cosines for any triangle, whether it's right or not right, because whenever you have a right triangle, this goes to 0. The law of cosines is the Pythagorean theorem when you have a right triangle. And that's because cosine of 90 degrees is 0. So this naturally just falls off because whenever you multiply by 0, you just have 0. So 2 times a times b times 0 is going to be 0, resulting in just the Pythagorean theorem. So although you wouldn't necessarily use the law of cosines for a right triangle, you can technically use the law of cosines for a right triangle. It will most likely just result in the Pythagorean theorem. So if you already know you have a right triangle, you might not even want to do the extra step of trying to cancel this out. Just start with the Pythagorean theorem and just use the law of cosines when you don't have a right triangle. But know that you can use it in either case. The law of sines, or the sine rule, needed to have a triangle that wasn't right. SOHCAHTOA needed to have a triangle that was right, and the Pythagorean theorem needed to have a triangle that was right as well. But the law of cosines is the most versatile of all of those rules. So we talked about what the law of cosines is, and in general and specifically when you're going to use it. Now let's actually use it. Let's put what we know into practice. Let's figure out how we can find our missing side x when we're given these two sides and the angle. Now this is our side, angle, side, triangle, side, angle, side. You see we have a sandwich with this angle between these two sides. So we know that we can use the law of cosines. And we don't have to worry about if it's a right triangle or not because it's going to work regardless. So let's jump straight into our formula. And it really doesn't matter which face you use because the faces are just to help you determine where you need to be in case you need to do more than one side. But we only have one side we're trying to find, so just pick whatever face you're most comfortable with. I'm going to do the c squared one. So c squared equals a squared plus b squared minus 2ab cosine of big C. And now that I have the formula I'm going to be using, I'm going to label my triangle. That's the first thing I want you to do, especially as you're getting used to this. Label your triangle so you know how you're going to be plugging things back into this formula. So if that's c squared, I'm going to say c is going to be over here, that x. So if c is over here, our cosine c is going to be this angle here is going to be this c here. So that's big C inside, little c outside. And it really doesn't matter where you put your a's and b's. So I'm going to put the a up here and the b down here. So now that we have our triangle labeled, let's plug everything back into our formula and see what we get. So we have x squared equals a, which is 17, squared plus b, which is 22, squared minus 2 times 17 times 22 cosine of 42. And this is 42 degrees. So I'm not going to put the degrees here because I don't want to keep writing that. But know that this is 42 degrees. And when you plug this into your calculator should be in degrees. Don't have it in radians. You're not going to get the right answer. We're dealing with degrees here. So make sure your calculator is in degrees. So now we're going to have x squared equal to 17 squared, which is 289, plus 22 squared, which is 484, minus 2 times 17 times 22, which is 748, cosine of 42 degrees. And when you plug in 748 times cosine of 42 degrees into your calculator, you're going to get 555.87. And when you add 289 to 484, you're going to get 773. So you have 773 minus 555.87, and that's going to equal your x squared. So when we combine these two, you have x squared equals 217.13. So you don't want to stop here because we want to find our missing side x, not x squared. So we have to find the square root of both sides. And when we do that, we're left with 14.74. Now, this is really an approximation. So I like to kind of keep putting that approximation here. We had to round here, so it's not even really an equals here either. So these are approximations. This is the last step where it was exact. However, notice when we do our square roots, we're not taking into account the negative. Whenever you do square root both sides, usually you have to do a plus and minus, but because we're dealing with sides, which have to be positive, we can ignore the negative. So our answer is 14.74 is our missing side. And approximately, because we had to do some rounding, round to the nearest hundreds here. That's not exactly 14.74, but we know that 14.74 would be approximately our missing side. So this is how we handle a side angle side triangle. Let's do a side triangle just to make sure we understand how we can use our formula in both cases. So here we have a side triangle in which you're trying to find a missing angle. So we're going to, once again, start with whatever face you want. It doesn't really matter. Just make sure you're consistent in your labeling your triangle so you know where you're plugging things in. So once again, I'm going to use the c squared one. C squared equals a squared plus b squared minus 2ab times cosine of big C. And I'm going to label this as such. Now it does matter where you put your labels here because you need to make sure your big C is opposite your little c. So this angle is opposite this. So this has to be my C here, and that has to be my big C. But A and B, once again, can be anything. So we have our labels, we have our formula. Let's plug everything in and see how it works out. So we have 4.9 squared equals 9.1 squared plus 8.3 squared minus 2 times 9.1 times 8.3 cosine of theta. So when we throw all of this into our calculator, we get 24.01 equals 82.81 plus 68.89 minus 151.06 cosine of theta. So now we have to get cosine theta, which ultimately we want to get theta by itself, but we had to get cosine theta by itself. So the first thing we do is let's combine these and shift them over to the other side. So 82.81 plus 68.89 is going to result in 151.7 minus 151.06 times cosine theta, and that's going to equal our 24.01. So we're going to subtract this 151.7 from both sides to get this by itself. So we have 24.01 minus 151.7 equals 151.06 cosine of theta. So now we have to divide both sides by 151.06 to get cosine theta by itself. So that cancels out on this side, and we have that over here. Now notice I'm not combining this, that's on purpose. I want to plug all of this into our calculator at once to get a more accurate answer. So since these canceled out, I'm just going to erase them from this side, and you see that we have a cosine theta equaling all of this. Well, in order to get theta by itself, cosine is a function, we had to apply the inverse function to both sides. So this is going to be cosine inverse, right, of all of this equals theta. Now you're going to plug all of this into your calculator just as it is, and remember your inverse might be like a second trig function on your calculator, but make sure everything is in degrees, but make sure you're using a cosine inverse and not cosine, and you should be able to get your theta to be the following. I'm going to just rewrite theta on this side so I can have theta equals something. And one thing to note, I almost missed this. Make sure you're checking your work, double check, triple check, I don't even care how many times you check, but make sure you check your work constantly because this negative, it disappeared. So make sure that you're actually carrying your negatives. You don't want to forget that. That was a negative there that when you divided both sides by this 151, that negative should have came with it. So this is going to be a negative 151 on the bottom here. Make sure you don't miss those crucial signs. It is so easy to miss, so make sure you're hyper diligent in checking that out. So now that we have our negative in the right spot, we plug all of this into our calculator with our inverse cosine, and we get theta to be 32.3. And this is degrees, so make sure you have your degrees here. Theta is going to be 32.3 degrees. This is our answer. And we rounded it, so technically it's approximately once again, but for our answer's sake, 32.3 degrees is our missing angle. So I hope you had to follow on today's examples, and I hope you see that the law of cosines really does complement the law of sines. When you have both of them, you can tackle so many more triangles. So make sure you get a good solid foundation in both laws, because that is going to help you better in the future. If you have any questions about what you saw here today, remember you can put them in the comment box below. I'd love to be able to help you as much as I possibly can. However, if you have questions about your own homework and below is just a little bit too small, feel free to visit me on Facebook at Tutor Me Sempai and tell me all about it there. If you haven't done so already, remember to leave a like. It really helps this channel get these videos to more and more people who could use the help. So I really appreciate it if you smash that like, smash the subscribe, hit the notification bell, and share this video with a friend. Well, that's all the time I have for today. I really hope this helped with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, and this is another session of Tutor Me Sempai.